So, all right, so today we're going to do, I got a new worksheet for you. Okay, so we're going to do some worksheet stuff at the very end, or whatever questions you guys want. But I'm just going to do a couple more things with sets. So today is going to be Cartesian products and power sets. So, so this is more operations with sets. So Puck did some stuff with you guys last time. I think Puck, so I think she might have said something like, so she might have distinguished, so let me just do a by the way here. So Puck distinguishes, I think, between these two. So for in this class, these will mean the same thing. For me. But apparently if you take a class with Puck, right, she wants these to be proper subsets, and these, could be, the two sets can be equal, okay? But for me, they mean the same thing. So I just wanted to explain this because sometimes notation from different classes will vary, okay? All right, so let's start with Cartesian products. Okay, so let me give you the definition. So let's let A and B be sets. So the Cartesian product or just product of same thing. So of A and B is the set, and then I'm gonna start. Well, I'll do it up here. Is the set A cross B, right? So sometimes we call this A cross B, but it's the product of A and B, and it's the set of ordered pairs A, B, where A is an element of A and B is an element of B. Okay, so this is the definition of the Cartesian product. It's a new set that we form from these two sets by looking at pairs. Okay, so some terminology. So the elements A, B are called tuples. Or ordered pairs. Sorry, ordered. So here the order matters. A comma B is not the same thing as B comma A. Yeah, I got it right here. So so those things are called tuples. Okay. So more generally, we can form higher Cartesian products. We can take the product of more than 3 sets. All right. So if A1, A2 through AN are sets, then this thing here, A1 cross A2 cross AN, so this is the set of A1, A2, AN, where AI is an AI for I is equal to 1, 2, all the way up to n. Okay, so that makes sense. It's a big conjunction of all these things. So that these guys are an element. So this is an element of A1, this is an element of A2, et cetera, and so on and so forth. So there's another notation for this. So we use this thing. AN. Okay? So this is means the same thing, but this is just the product symbol. Okay. There's also and then there's a special case of this, is that when A1 is equal to A, A2 is equal to A, they're all the same thing, and AN is equal to A. So A to the n, this is the nth power, this is just going to be defined to be this, and this happens n times. Okay, so this is a power of a set. So this is called the power. This is a power of a set. Okay. Okay, and sometimes when we write the cross symbol, we'll just say like A, so like I'll write, instead of saying the product of A and B, I'll write A cross B, something like that. Okay, it has nothing to do with cross products or anything like that, it's just another thing, yeah.
So are tuples the same kind of tuples in n tuples dealing with like
yeah, for sure.
r and like n dimensions?
Yeah, this is an n tuple here.
Okay.
Right, exactly. Yeah, this is an n tuple. Right. This is also a tuple, an n tuple. Right. So yeah, they're the same thing. Tuples of elements. So let's do examples. Examples of products. So R2 is R cross R. So this is one that you guys are familiar with. So here we're just looking at the set of x, y, where this is one copy of R and this is another copy of R. It's useful to visualize sets as like thinking about it as two axes, okay, when you take a product. You can do R3. This is R cross R cross R. Right? So there's a point in there. And so this is a three-dimensional space. Right? So we have this. So you can have a point here that's like x, y, z. Right? So I'm trying to show that it has 3 dimensions to it. But these are pairs of ordered triples consisting of 3 elements. And you can continue this process. You can do R4, R5, whatever, right? So it doesn't matter. It's just a math thing, right? So R4, so it gets harder to draw. Right? I can't really draw this one, but we can still consider it. W here, so this is X, Y, Z, and W. These are all elements of R, right? So you can't draw this anymore. There are ways of visualizing them. Okay, I mean, I guess you can do this. Let me show you one way you can draw these, right? All right, so if I take something in R2, you can take a base point to be x, y, and then the 2 other points here, so this could be a vector represented by zw. So these are points with vectors attached to them. So that's one way that you can visualize it. Okay? There's points with arrows. Okay, so it's the collection of all points and arrows. So x, y, z, w would be the whole thing. Okay, but you can't really draw them in general. But you can make cartoon pictures, which is helpful sometimes. I guess you could do 4, you could do Rn. So this is like x1, x2, xn, where x1, x2, xn, these are all just real numbers. So this would be an n-dimensional space. Okay, so this is, so it's like the same thing. You can just keep going. Okay, so let me do another example. Okay, so if A is the set 1, 2, and B is the set E pi, and then we'll do the set 1 like this. Okay, then A cross B. So this is the set of AB, right, where A is in A and B is in B. Right, like so. And this is the set. So we'll take one from A and then the other one from B. 1 E, 1 pi, 1 in the set consisting of one element, which is 1. All right, and then we have 2 E, 2 pi, and 2 with this one element set 1. Okay? So you'll notice here that how many elements does this thing have, right? So this has 6 elements, this has 2 elements, and this has 3 elements. So 2 times 3 is 6. So the number of elements in this product is the number of elements in here times the number of elements here. Okay, so that's kind of a useful thing. So let me do another one. What's B cross A? A cross B and B cross A are not the same thing. Okay, B cross A. So this is the set of BA, where B is an element of B and A is an element of A. Okay, and so this is the set, and then we start with elements of B. So we do E1, E2. The order in which I write them doesn't matter, so I could permute the list of elements in this set. It doesn't really matter, but the order in the tuples does matter. Okay, pi 1, pi 2, and then we have this set 1, 1, and then we have the set 1 and 2. Also a 6-element set, but so I just want you to observe that A cross B is not the same thing as B cross A. Okay. All right. Yeah.
Can I say A cross B is symmetric with A cross A with y equal x?
No.
Because they're the inverses?
They're not. There's oh, what do you mean? Like so if I yeah. So there, if I were to take all the elements, yeah, maybe. I think I didn't see what you're saying. Yeah. So if I take all the elements of A cross B and I were just to flip them, then I get all the elements of B cross A. Yeah. So there was actually a map between this one and that one, and we'll talk about that by flipping the elements. Yeah.
Is it sort of like oh, so it is. Okay, I didn't see the last line there. Like it's like matrix multiplication, where like the orders matters and like.
Yeah, the order matters for sure. The order of Cartesian products matter.
And that's why
I mean, they matter like this, but like he said, they're similar in the sense that if I take A cross B, I could get B cross A by just flipping the elements, right? So there's a kind of a correspondence between one and the other. There's actually there'll be a function from one to the other which is invertible, right? But they're on the nose. They're not the same, right? They're the same up to flipping. Okay. So the book gives a proposition. Which states the basic properties of these sets. But I want you guys to prove a lot of them. I'm gonna start you guys on this. So this is the end of the examples here. But I want to do some more. So I want to talk about some properties. Okay. So. And so I think this starts you on your homework, and this is proposition 4.2.9 in the book. Okay, so we'll let A, B, C, and D be sets. Okay, and I'm going to state some properties. So A cross the empty set is just the empty set, which is the same thing as the empty set cross A. So the other properties are like A cross B union C. This is the same thing as A cross B union A cross C. Okay, the other things that we're interested in are like A cross B intersect C. So this is A cross B intersect A cross C. Right, 4. So we could do A cross B intersect C cross D. So this is A intersect C cross B intersect D. And the last one here, you could do A cross B union C cross D. Okay, so this one, you'd expect me to write maybe equals like I've been writing the whole time, but that's not true, right? This is A union B, or A union C, cross B union D. So this is a subset here. We only have a subset. We actually don't have we don't have equality in general. Okay, so this is note that this is not equality on this one. Okay, so you kind of have to be careful a little bit about just like distributing operations and such. Okay, so we don't just get whatever. You know, I mean, you don't just get to distribute the cross product freely or these intersections. Okay. I guess it's not really distributing, but it's well, this one's a distributive property. This one, I guess, is I don't know what you'd call that. All right. Okay. So let me show you how to prove one of these, so that you guys can get started. So let's do the proof of the second one. Okay, so the proof of the first, let me just say something about the proof of the first one. So this is A cross nothing, right? So A cross nothing is nothing. That's the idea of this. Okay, so all right, but this one, let's do this one. So there's two strategies. Okay, the first one. Okay, the first strategy could be show that they're equal as sets. You know, show that the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. Okay, so we show that this thing is a subset of this, and this is a subset of this. Does that make sense? So that's like the usual. This is the usual. This is as usual for equality of sets. Okay, and this is kind of the safe strategy. All right, the safe way to show them that they're the same. Okay, so the other way is to show the propositions that define the two sets. The two sets are logically equivalent. Okay? So they're both fine. I'm going to do, and they're both pretty much the same thing, except for this one here is really kind of like writing this one out in words. Let me show you what I mean by the second one. So proof via the second. So via the property B, or the second strategy. Okay? So what do we need to do? We need to show that if there's an element here, it's this, so an element here is exactly the same thing as an element here. Okay? So xy is an element of A cross B union C. We're doing union right now. Union C. Okay? So this proposition here, this is equivalent to the proposition that x is an element of A and y is an element of B union C. Okay, so those two things are logically equivalent. That's what it means for this to be here. That's what it means by definition. Okay? Okay, and so what I can do, what can I do to break this up? Yeah.
Y and B.
Or
C.
Yeah, exactly. So this is the same thing as x is in A and y is in B or y is in C. Okay, so that's this thing. All right, what can I do now? Yeah.
Could you distribute them?
Yeah, let's just distribute them. So this thing distributes over. So this is logically equivalent to x is an element of A and y is an element of B, or x is an element of A and y is an element of C. Okay, what can I do now?
Reduce it back to A, B is A cross B, and AC is A cross B.
Exactly. So this is the equivalent of saying that xy is an element of A cross B, or xy is an element of A cross C. And what can I do now?
Rewrite it as your original.
Rewrite it as a union, right? Yeah. So now we can just rewrite that as a union. And so this is equivalent to, so xy is an element of A cross B union A cross C. Okay? So this showed that, this proved that this statement here was logically equivalent to this statement here. So this proves that xy, if and only if, is an element of A cross B union A cross C. Okay, so the sets are equal. Does that make sense? Yeah.
I just have a question with the unions.
Uh-huh.
So you're allowed to go from a union to an or that's kind of like what the union means?
Yeah, union is exactly what an or. So that's what union
You
is.
use them interchangeably?
Well,
Like,
I mean, so yeah, so so regarding your question, X is an element of S union T if and only if X is an element of S or X is an element of T. That's the definition. This is by definition. That's how we define the union. The union was where this held, right? Does that make sense? So that's how we define the union. So it's really, we're just redoing, when we're doing sets, we're just redoing propositional logic in another way. So sets and propositions are really the same thing. Yeah?
Yeah, so this would be like similar to the questions you had us do a couple of weeks ago of the implications of R, Q, and S, and kind of like rewriting one side to the other, except we just have to be mindful of like the unions and what.
Yeah, exactly. That's exactly. It's pretty much the same thing as what we did with propositional logic, right? Except for, you just have to do it in terms of the language of sets. Yeah. So union will turn into or statements, intersection will turn into and statements, complements will turn into not statements, right? So yeah. Okay, so you just kind of use those properties. Does that make sense? Okay. Okay. So yeah, and so I think I had you guys do the other properties on the homework. Okay. I'm not sure of all of them, but some of them are on the homework. Okay. And so note for this one, you should be able to find an example, right, where that doesn't hold. All right. let me do power sets now. All right. Okay, so definition. So let X be a set. So the power set of X is the set. Okay, and then I'm trying to do a fancy P. Let me do a fancy P. Okay, let me just do, there's a fancy P of X. Okay, this is the set of A such that A is a subset of X. So it's the set of subsets. Okay, there's another notation that sometimes you'll see people use. Some people write 2 to the x for the power set of X. All right, does that make sense? So it's just the set of all subsets. That's the power set of a given set. All right. So let's do an example. Okay, so let's let X be the set 1, 2, 3. Okay, so for subsets, you kind of do one thing and then you do the other thing. Okay, so 1, 2, 3. All right, so let X be this. So let's enumerate the subsets. Okay, so what's a subset of X? What's the smallest subset of X? That's one of them. 1. 1 is 1. Okay, you also have 2. You also have 3. I'll just write them like this, and then I'll collect them. Okay, what's another subset? 1, 2. So let's write 1, 2 down here. What's another one? 1, 2, 2, 3. We'll do 2, 3 over here. Yeah, 1, 3, 3, 1. 3, 1, this is the same thing as 1, 3. Order doesn't matter for sets. 1, 3. Okay? So we have 6 other subsets. There's 2 more.
1, 2, 3.
1, 2, 3, the whole set itself. 1, 2, 3. A set is always a subset of itself. What about, yeah? The empty set. You stole his thunder.
Why are they equal now when they weren't equal before? So it's like.
So one was tuples. These are sets. Yeah. So ordered tuples, these are unordered sets. And you can't have repetition here either. No repetition allowed. So if the set of 1, 1 is the same thing as just the set 1. Yeah, Tyler.
So does the empty set always have to be in the power set for any given?
Yes. Yeah, the empty set is always a subset. Because remember, it's like this. So I think Puck maybe showed you this. The proposition is like false implies anything, right? And so false, when you have false, so P implies Q is always true when P is false. Okay? Yeah. Because it was not P or Q is the equivalent. So let's write down what the power set is. So the power set of X, so this is the set consisting of the empty set, the set 1, 2, 3, and then we have these 2 element sets, 1, 2, 1, 3. And I'm going to continue on to the next thing here. So this is the set 2, 3, 1, 2, 3. Lots of curlies, okay? So this is the power set of the set X. So it's the set of all subsets, right? Notice that this is not the same thing as 1, right? So 1 is not an element of here. So note that like 1 is not an element of here, but the set of 1 is an element of here. Does that make sense? Okay. So it's a set of all subsets. So they have to have a fancy little braces around them to be involved. Okay?
But if it's in sets, we do not allow repetition.
We do not allow repetition.
But initially we have the same elements. I mean, if you expand all those sets inside it, you'll get exactly the same elements.
Yeah, but that's not what we're counting. We're not counting the elements in this. We're not counting the elements of this set here. We're counting the subsets themselves, right? So these guys are not the same, right? This is the set of 1. This is 1, right? This is the set of 1. This is 1. So yes, if I were to take the union of all the elements in the power set, I would get the set back, but they are not the same. Yeah. This one, the empty set. Empty set.
It's a set, an empty set.
Uh-huh.
It's a subset of 1 include empty set.
Isn't the
Is the empty set's a subset of this? Yeah.
Yeah, I mean, it's the empty set in the area.
Any set contains the empty set as a subset. Even the empty set has the empty set as a subset. I think this was talked about last time. That's one of the examples. The empty set, so empty set's a set. The empty set's a subset of every set. So the empty set's a subset of the empty set. All right? So yeah, that's another example. Let's do another example. Okay, so if X is the empty set, then the power set of X is the empty set. Okay, that's kind of a weird one to think about. Because the only subset of the empty set is the empty set itself. All right. Okay, so let me do a proof here. Let's do a proposition about the, so you can do propositions about the power sets. So like if A is a subset of B, so here's one. Here's a proposition or lemma. Okay, so let A and B be sets. B be sets. Okay. A being a subset of B implies that the power set of A is a subset of the power set of B. Okay? But this is also true that the power set of A being a subset of the power set of B implies that A is a subset of B. So this is the obvious direction, right? And this is the not so obvious direction. Okay, so this is a lemma here. So let's do the proof. Okay, the first one here. So suppose A is a subset of B, and let A prime be an element of the power set of A. Okay, we need to show that A prime is a subset of B. Show A prime is an element of the power set of B, or which is the same as A prime is a subset of B. Okay, that's the definition of what it means to be a power set. So if A prime is an A prime here, then, well, okay, so let me actually write it like this, right? So we're given this, and we're given this, right? Sorry. So we're given, sorry, we do need to show that, what are we doing? We're doing this one. It's almost a tautology, right? So, so we're given a subset A prime. Okay, so we have A prime in here. We actually are given that, Oh, we need to show that A prime is an element of B. Okay, but since what am I doing right now? I'm not saying this well. Okay, yeah. So we suppose that A prime is in P of A, and we need to show that A prime is in P of B. Okay, so let me just write it like this. Okay, so this is the same as well, A prime is a subset of B. Okay, and A prime is a subset of B if and only if for all A, well, let me do it up here. Okay, so what are we doing? A prime is a subset of B if and only if, oh, so, I mean, we're given that, okay, so we're given A is a subset of B, and A prime is a subset of A. So what property can I use of subset inclusion here? So it's a partial order. So by the transitive property, A prime is a subset of B. So we have this is a subset of this, and this is a subset of this, so we must have this a subset of this. Okay? Yeah?
Maybe not using the properties, but looking at the second bullet point you have on the last board, is it kind of saying that if all the collecting all the series of X, and that's a subset of all of B, so A has to be in B somewhere.
Yeah, that's the idea. I'll prove that part right now.
Okay.
Yeah. So now let's prove the second part. Let's prove the second bullet. Okay, so suppose that P of A is a subset of P of B. Okay, and so now this is what we're supposing, and so we'll let A be an element of A. Okay. So since A is an element of A, this means this guy here is an element of P of A. Okay, and since P of A is a subset of P of B, this gives the single element set A is an element of P of B. Right? Okay, and this means that, by definition, that this guy here is a subset of B. Okay? And so and that means that A is an element of B. Right? In particular, every element of this set has to be an element of here. So we started with an element of A, and we concluded that A is an element of B. Okay, so this shows A is a subset of B. Okay, so this was the assumption that we started with, and then you start with always, to show one thing's a subset of another, you start with an element here, and you have to show that it's an element here, and that's what we did. Okay, so you just have to use the rules. Yeah.
For the first bullet group, you say that A prime is a subset of B, right? And you also said A prime is included in PA, which means all elements in A prime will be set.
Yeah, all elements of, sorry, A prime is an element of this,
Yeah.
which means it's a
Oh.
subset, right? So of the elements, yeah, so that's a good thing. That's the thing that you have to check for, right? Is whether or not, so what he was saying, he was worried about whether the elements of A prime were sets or not, right? So if the elements of A prime were sets, then it wouldn't really parse to show that, to make sense of like A prime being a subset of A, right? Yeah.
I just kind of have a question. So when you have the set x is equal to 1, 2, 3,
Yeah.
could that be thought of as maybe something in like 3 dimensions or 3 space, and then when you have 1, 2, and 3 alone, that could be, so like if all the subsets of like 3 dimensions could be like lines or planes or all 3 space, like the 1, the 2, and 3 would be like points.
The vector spaces?
Yeah, and the points would be like 1, 2 would be like a lot. Like you're kind of like there's smaller parts of 3 like.
So I think what you're getting after is that those are both partial orders. So subsets. So like here, yeah, and it's the same. It's something that's similar to this, but here we kind of have we have this inclusion. We have these inclusions here, right? And I mean, if you're thinking them, let's see, this one's not there, but here, I guess it goes here, right? So I guess we have this one to here, and this one to here, and this one goes to here, and this one goes to here. Okay, so I'm just going to write this little like hook arrow thing for. Okay, so this one, so there are relationships between how these things are nested among each other in vector spaces, but it's not exactly the same thing. I mean, they're both part. I think that you're saying that they're both orderings. They're both partial orderings. Yeah, and so that is a way to think about it, but.
Okay, so like the one, like they don't necessarily have to be in order. I guess like my question is like the 1, 2, and 3. They're not like separate components or just pieces like I, J, and K, where like it just happens to be a set of 1 common, like all the ways you can arrange those. I don't know.
Yeah, yes, I mean, yes and no. There are like ways to think about them so that vector spaces, like the orderings here will be similar to the orderings for vector spaces, yeah. But I mean, it is an ordering, yeah. So if it helps you to think about that type of thing, then yeah. Yeah. But I mean, if you're not thinking about that thing, that's totally fine too, okay? I just thinking of them as subsets. All right. Any other questions about these things? This one's kind of, yeah, it's kind of weird, right? This one that you have the power set, and then that shows you that the sets are the same. Okay, so let me give you guys the handout now, and then I'll write up some exercises here. So let me see which ones I picked out for you. So let me pass these around. It's also online. Maybe you can help me with that. Okay, so for exercises, so the teching of it, it's got some typos, so I'm gonna fix it. In particular, the numbering's a little weird. Okay, so let's do so section 2. Let's do E and F would be a good one to start, and then let's do section 3. I. So A, the first one. Okay, so. All right.